All right, we are on the last theorem, theorem 9. And what do we deal with in theorem 9? In theorem 9, we deal with what is called the Tan-Chord Theorem. This is the famous Tan-Chord Theorem. And do yourself a favor. I want you to pay attention to this theorem. Why? As my student Obela observed, there is no Euclidean paper that you're going to write that does not include Tan-Chord Theorem. No paper. Check your past exam papers. Tan-Chord Theorem will be there. Right? So what does it say? Now, we have got a tangent here, ABC. And this tangent ABC, if you check on the right side, here we've got BD. Line BD is a chord. And the line that is subtended by this chord BD is angle what? Angle E. So the angle which is outside this tangent, or outside this chord, sorry, where the chord and the tangent meet, if I call it angle X, it will be equal to this interior angle where there is E, then it's X. But also on the left side, you have got this tangent AB and you have got chord BE. So this angle here, if I call it Y, it will be equal to what? To angle D. Right? But if you observe here on top, I wrote acute-angled case. Why? Because theorem 9 has got two different cases, the acute-angled case and the obtuse-angled case. So I want to prove to you to say that actually these angles, they are equal. You know, the tangent and the angle which has been formed by the chord. So what are we going to do to prove that? Here at the dot, we have got what we call the center, right? So I'm going to construct a line here. Now, there on top, I'm going to call it point F. And if you check, if I move from one end of the circumference through the center to the other end of the circumference, what do I have? I've got a diameter. So I have a diameter here, BF. So now I didn't have point F. Now I say join BF. And BF is a diameter. Now I'm going to join point E with point F. Right? I've joined them. Now, if you just look at the diagram, you can see that here we've got 90 degrees. We've created a right angle. Right? So now, what's happening? Remember from your theorem 3, you are told that an angle in a semicircle is equals to 90 degrees because we've got this diameter BF and now there is an angle that has been subtended here. Now we've got 90 degrees. But what am I going to do? Now, temporarily, I'm going to remove this X here. And I will put angle 2, and this is angle 1. So now I've got angle E1 and angle E2. Right? And here, where there is X on the B, I'm going to remove it, and I will put a 2 here. And here I'm going to put a 1. Now, what do I want to remind you of? Because a lot has happened with the construction of this diameter and this chord, but this and this chord. But I've explained the chord. I've explained that we've got a right angle there. Now, what is missing is this side. Let's remember, this dot which I'm remaking is a what? Is the center. And from the center, let's call it point O. From the center to point B, this is what? This is a radius. And there is a tangent. So a tangent which is perpendicular to the radius gives us 90 degrees, which means that angle B1 plus angle B2 is equals to 90 degrees. But now, how does that help us? Now we start to talk about the fact that angle B1 plus angle B2 is equal to 90 degrees. And we say that tangent which is perpendicular to a radius. Then we come here. I'm now documenting what I explained earlier on. Angle E1 plus angle E2. Angle E1 plus angle E2 are, those two angles are equal to what? To 90 degrees. And my reason, angles, or angle rather, angle in a angle in a semicircle, right? So I've got two reasons here. First reason and second reason. I have proven that this entire angle B1 and angle B2 is equal to what, or equivalent to angle E1 and E2 also. But now there is one more icing on the cake. What is that? Remember, I've told you that you must rotate your what? Your diagram. So this is what I'm going to do. I'm going to rotate. I want you to observe this chord FD here. I'm going to mark it. Actually, let me highlight it with a different marker. I have got this chord FD here. And this chord FD here, what is its relevance? If I'm to follow the points where it went, this is line F, it went to point B. This is line D, it went to point B, which means that it subtended this angle B1. And if I check again, this point F went to point E, this point D, it went to point E, and they created what? Angle E1. So these are angles which we say that they are in the what? In the same segment, right? Mean to say that angle E1 is equal to angle B1. So I come and I write that angle E1 is equal to angle B1. Right? So basically what's happening here? Do you see now what happens? Check. If I come back to angle B2 here, which is here where we started, we had said that angle B2 here, I had labeled it X. And I said that there was this chord here. And this chord BD, it subtended angle what? E2 here. Right? Which is X. Do you see that when we're having B2 and B1, I managed to prove that E1 and E2 combined, they were also equal to this. And I also, lastly, I proved that E1 was equal to B1. So what did we do? We removed this and we removed that, and we are now left with these two angles. And because prior to that, I had proved that they are equal, it now means that angle E2 is equal to angle B2. So now I come and I conclude that, therefore, angle B2 is equal to angle E2. And my reason, I say Tan-Chord Theorem. So when we say Tan-Chord Theorem, is just a shortcut, but this is the proof of how we came to that theorem under the case of what? An acute angle. All right. Now we move to the what? To the obtuse-angled case. The obtuse-angled case, don't forget that to say that your obtuse angles are angles that are more than 180 degrees. So what is the first step? The first step is to observe that, oh, okay, here what do we have? We have got this tangent. Camera. We have tangent what? ABC here. We have this tangent ABC. And what's happening with this tangent ABC? It means that this angle here, where there is AB, this part here, it is equal to what? It is equal to angle D, right? So this angle here is equal to that angle. So, all right, what are we going to do now in this case? The camera, it's not doing what I want it to do. Okay, now it's fine. So the first thing which I'm going to do, here I've got a center here. I'm going to label the center, that is O. I want to prove that this angle here on the tangent, it is equal to that angle. Why? Because it was created by chord EB. All right, so what do I do? Now I'm going to join O to B. And I'm going to create a point F here. Then I say join OB and OF, which is what I created. But from there, what am I going to do with point F? Here, I'm now going to join point F to point D. Here. So I say join F D. Everything that I was not provided, I'm informing the examiner about it. Now check. FB is a diameter. FB is a diameter, and we know that if FB is a diameter, it means this end is a semicircle and also that end is a semicircle. And there is an angle now where I joined FD. This angle here, let's call it D1, and this tiny angle there, we call it D2. So it means that angle D1 is equal to what? Is equal to 90 degrees because it is an angle in the semicircle. So now I come and I say angle D1 is equals to 90 degrees, and I say angle in the semicircle. But remember, here where I am having the center here and I joined what? I joined OB. What happens? This dotted or the broken line that I have here, I created 90 degrees there. So let me call it B1, and that one, the smaller angle, I call it B2. So now I say angle B1 is equal to angle B1 is equals to 90 degrees. But remember, my theory was saying that the entire angle D is equal to the entire angle B, meaning to say the entire angle B is B1 plus B2. And so far I've proven that B1 is equals to D1. So what's left for me is to prove that this B2 is equal to this E2, right? The E2, the tiny ones. All right, so what is it that I do to prove that they are equal? I simply get to what? I get to rotate here. When I rotate, my diagram is not really showing exactly what I want you to see, guys, but it is about point what? This coin